Thank you everyone for joining us for this tech talk organized by Riwers. Also, thank you everyone for joining online. Today, Lubo will have a very interesting topic: deploy your app on Kubernetes in 1 hour. And important part, if you have any questions, we'll be posting a link in the chat. So you can then use Slido to ask any questions that you have. And in the end, we will then go through them and we will ask Lubo what you are interested in. So,
Okay.
Thank you very much. Thank you, Lubo. And let's get started.
Okay. Thank you, Adam. So again, thank all of you for joining us. Basically, this presentation is called Deploy Your App on Kubernetes in 1 hour. But what we will actually be doing, it will be kind of the journey from code to a deployed infrastructure, showing multiple ways on how you can deploy your applications in the wild for production or for development. So let's start with some trivia. Well, some time ago, it used to be quite simple. You as a developer created your code. You just pushed it to some shared web hosting or some server where your application was running. And from there, it went directly to the target audience. That's how it was. Most of things were done manually. Most applications or most web applications were developed in PHP, which is a server process language. So it was basically just about placing the files on a hosting and everything was done. Or you would deploy your applications on virtual private servers or bare metal servers. So there was like no automation. It was quite simple and straightforward. But we should complicate it. And there were needs for, let's say, different environments. Now it is quite normal for every development team or every application to run multiple environments. For example, we get a development environment, which is usually consumed by developers. Then we get a staging, which is consumed by testers or by QA engineers. And then we usually get a production environment, which is, well, then consumed by the target audience. Now we're talking about the same application, which is deployed 2 or 3 or 4 or 7 times, because that's just the base isolation for development, staging, and production. But you may get as many of environments as you like for different feature sets or some special branches. You have no limits here. Other problem that became quite common with applications which run in shared runtime. So we're talking, for example, Python applications or Node.js applications. Was it didn't work on PC of the target. Yeah. So there's a difference. Your PC could be running Ubuntu with PostgreSQL 12 as a database, with Python 2.9, Node.js 14, and there's your application requiring all of these components. But when you transfer it to the target, which, let's say, runs macOS on a different CPU architecture with different versions of these packages, it might not run as well. There are several differences that there could be between PCs or virtual machines. One of them is, for example, CPU architecture, where you might get standard AMD or x86 architecture, or you might have ARM processors. There's difference in operating system, differences in kernel, well, differences in system libraries, which are in the user space of the operating system. And then we get to the runtime. So there are the, virtual machines which run your applications that with Node.js, Python, Java. And you have differences in application versions, like databases, caches. Yeah, there are a lot of things that could go wrong. So that's why we have containers. But to begin with, what's the difference? In traditional deployments that we were talking about before, you had some hardware, like your computer or server, which ran operating system and run all the applications side by side in the user space. Then we evolved towards virtualized deployment, where we use virtual machines on top of one operating system. So basically we created more computers within one physical machine. And then it evolved even further, and there were containers. Containers work on the way they share the same operating system, the same kernel, but are separated on user space level, so the applications are isolated. Now I have an example here, and basically this is, for example, the your application and the stack it needs. It needs Python 3.12. It needs some Python libraries. What we want to do is to create a container image. So basically package this all together so it can be taken as a one piece and deployed somewhere else. For this, we have something that evolved from Docker. I believe many of you already heard about it, and that's called Dockerfile. Dockerfile is basically a definition of the environment. Let's just go through this line by line very quickly. As you can see, you have the first line which starts with from. You will define what kind of environment you want. It's basically the base image. You can choose different programming languages, different environments, different distributions. For example, here it's Alpine. And then this file is executed in a sequence. So first thing we do, we create some directory within the container. Then we switch to it. That's the work there command. We copy all we need from our source repository to the target container, and then we run some commands. For example, here we install some libraries, then we install the packages required by our application, then we do some cleanup so it's not too big, and at the end we define what command should be executed to launch your application. So basically this is image of entire environment for your application with your application built in it. What you do is you build this. When you build this, you create a container image. After you've done this, you push it to a container registry, which is a public resource, for example, Docker Hub or GitHub container registry, or you can host your own. And from the container registry, this image is consumed either by developers or ordinary users, or it's installed on target platforms, servers. It can be Kubernetes, it can be, well, various environments. We'll talk about it in a while. So containers isolate user space resources from kernel. What does it mean? That they basically create safe sandboxes within operating system, and all of these applications are able to run in a separate environment without unwanted access between them. This includes networking, file system, process space, and yeah, basically most of the aspects are isolated. This also creates a very convenient way to create pre-configured and preset environments. This gives you the ability to completely specify what is required by your application. Also, it allows for very simple sharing or distribution of applications packaged completely. We go here, so we build our image, we pushed it to registry. Now what we can do with it? First, anyone can pull this image and use it for either further development or just consume it on their own in a way they find fit. You can run it on any Linux machine, basically using Docker engine or another runtime which can do this containerd. And then there's Docker Compose, which uses Docker engine, and we'll be talking about it a bit more later. But the important and most interesting part is that you can run it on any platform, which can provide full 24/7 environment for your application. This could be Kubernetes, this could be running Google Cloud Platform, this can be run in AWS in several ways. For example, using Elastic Container Service, which just runs your container and makes it accessible to the world. Or using EKS, which is Elastic Kubernetes Service, so you can provision your cluster in AWS and run your applications over there. Or EC2, but with a simple Linux machine and running in Docker engine. The same applies for DigitalOcean. You can run it either in a virtual machine or you can run it in a managed Kubernetes cluster. So containers, container runtimes are Linux-based subsystems to run containers. It's quite simple. And this technology is supported by various on-premise solutions, private and public cloud infrastructures, and the containers are ready to be deployed everywhere. So that's why it's so convenient and so widely used these days. Now, there is a simple way to do this yourself, and that's Docker Compose. Docker Compose allows us to create infrastructure as a code-based description of infrastructure you need for your application. Because it's not just your container and your application. You might need database, you might need some cache, you might need some third-party services for your application. So this is basically the easiest way to do this. You take your application, you take the packages that it needs or the other containers it needs. Let's say it's Postgres and Redis in this case. And you write a very simple, several tens of lines long piece of YAML file like this, where you define in a very simple way that you would like to have a database running from this public image. You attach a volume to it so you don't lose your data. The same applies for the Redis instance. And then you will just add your application to the mix. Basically, this creates a complete infrastructure with resources that are mixed together on the network level, so we can easily connect these services. And basically, this creates an isolated bundle of multiple running containers on your machine or on any other target machine where you'd like to run this. So it's a very convenient way to describe infrastructure for a smaller scale mostly. It's perfect for quick environment sharing. So if you're a team of developers, you can just prepare a development Docker Compose file with your application included, and also other containers it might need, other services. And you just put this to your Git repository, and other members of your team can easily start up the development environment. It's also suitable for smaller or small to mid deployments on virtual private servers or virtual machines anywhere in the cloud or on-premise. And it can also be extended by Docker Swarm, which is basically a very simple platform that allows you to distribute this workload among multiple virtual machines or virtual private servers. Now, we're going to switch a little. Now we were talking about Docker and infrastructure as a code. Now we're going to talk about how to most efficiently transform your application into a container image so you can use it in your infrastructure later. Here come CI/CD pipelines. CI/CD pipelines are pipelines of code which are run by your source control provider. This could be GitHub, this could be GitLab, this could be Bitbucket, Azure DevOps. All of these providers have their own CI/CD system. The CI/CD tooling or CI/CD system, what it does is it picks up changes in your source code and runs a sequence of commands or processes over it and automates a lot of things. For example, this is a sample pipeline which consists of 4 steps. First of it, it's linting. So let's say it validates that your code looks the way it should. Then it, let's say, build it. If it's compiled application, then you can run automated tests, compute test coverage. Let's say if this fails, the pipeline fails, so you don't deploy application that didn't pass the requires tests. And the one that we'll be focusing on is the publish stage. In publish stage, the application is taken together, packaged. In our case, it will be using Docker, and pushed into a registry. You can imagine all of these steps like a piece of code or a running executable that you can basically program yourself in a way you want. It's not limited to these cases that I've listed here. You can do whatever you want with it. And yeah, so we'll be running a CI/CD pipeline which builds our package, publishes it to container registry, and there we will have our container image.
Yeah. And I would like to remind everyone that we are using Slido actually.
Sorry.
Just so please, who is in the room, scan this QR code right now, and you can ask your questions. And everyone who is online, then you can just click on the link which is right now in the call and use it. So I will give you like 20 seconds Lubo can breathe at least.
Oh, I'm gonna have some water.
I have some water, yeah. Okay. Let's wait a second. All good? Then let's go back to presentation.
Okay.
Thank you.
Let me continue ranting then. So CI/CD pipelines, basically, we can use CI/CD pipelines to carry out a lot of tasks. Some examples are listed here: code linting, build, testing, packaging, publishing, and even deployment. The CI/CD pipeline can also deploy the application for us. But yeah, that's just one of the cases. And as I said, it's provided by most source control providers. And if you have a source control provider which doesn't support this, you're using wrong source control provider, of course. So now let's talk a bit about the target topic, and that's Kubernetes. What is Kubernetes? Kubernetes is a distributed environment to run your workloads, and Kubernetes is a resource manager. What that means, we will talk about in a while. The very basic thing is it's composed of two things. The first thing is the control plane. All of the every node you can see here is basically a virtual machine or a physical server. And the control plane is responsible for taking care of all the information within the cluster and for taking actions so that your applications are running on the worker nodes. So yeah, we'll be talking a little more about what's inside the control plane and what's inside the workload part of the cluster. The very important thing is that, yeah, it can be seen as a deployment management and automation system, a distributed platform. But it's also very important to know that basically Kubernetes is a resource manager and controller or orchestrator. It's very extendable and it can be used on cases beyond way beyond deployment of applications. What's the very important part? It can scale to high number of nodes. So basically you can create vast infrastructures and you can run thousands of containerized workloads. It's built on the principle of reconciliation. What this means is that you just put in resources in the cluster, and the controllers within the cluster are responsible for making things happen in the background. So the entire infrastructure converges to the state that you described in your resources. Now, here's an example of how a control node looks. These are the base components of a Kubernetes. First of it, it's etcd. This is the only stateful part of the control plane. It's basically a storage. It's a database where all the information that you put in are stored. This is a pet. You really want to take care of it all the time. Then there is Kube API server, which is, well, API server that makes all of these resources accessible, provides authentication, authorization, and gives access to these resources to either system administrators, developers, and also to other components running in the cluster. And there is Kube Controller Manager, which actually takes care of all the internal things. It runs loops, which watch resources, and it takes actions. Then there's Kube Scheduler. That's a very important part. Let's say you have 5 or 8 worker nodes, which have some hardware configuration, so some number of CPUs, some amount of RAM, some storage parameters. The Kube Scheduler is responsible for taking the workloads you want to run and placing them on these machines in a way that they have the space and basically all they need to be run properly. Also, it takes care of distribution. So if you want to run 5 replicas of your application because you're expecting a high load, Kube Scheduler is responsible for placing them in on different nodes. And then finally, there's Kube Proxy, which is basically a network proxy that takes care of communication towards your services, and it makes sure that this load is balanced, that all of the pods running your application are saturated in a weighted manner. And there are worker nodes which will run your application. So in this example, I only put there your some application server and a database. Kubernetes is a highly modular platform, and basically you can take two approaches when you want to start with it. One of these approaches is to go with vanilla Kubernetes. That means that you'll be setting it up completely on your own. You can do this on virtual machines. You can do this on bare metal, so on physical computers or physical servers. But comes at a cost of very increased complexity and a lot of choices you have to make. This is the do-it-yourself approach, and yeah, I would really recommend this if you want to learn the really what's under the hood. The other option is to use managed Kubernetes from AWS or Google Cloud Platform, DigitalOcean, and when you do this, the most important parts are taken care of for you, and these are container runtime interface. Yeah, you can run the containers using multiple tools, multiple runtimes. This could be the Docker engine we were talking about. This could be Containerd. There are several of them. There are some differences between them. You have to choose. When it comes to networking, it's get even more complicated. You have tens of networking stacks you can run, and it really depends on the needs you have and on the infrastructure you're going to be running this on. And when it comes to the choice, yeah, well, third time might be the charm. So you might end up rolling out 3 networking interfaces before you find the one that really suits you. And when it comes to the storage, it's a total hell, because that's the most complicated part, and that's a big benefit of managed Kubernetes, that you don't have to care about this. So, well, we were talking about Kubernetes being a resource manager. All of Kubernetes resources are represented as a JSON or YAML files that have predefined structure. I'm going to show 2 examples and tell something about it. For example, this is an example of config map. The first line you see is API version, where it's kind of a group to which the resource belongs. Then you have kind. For this sample, it's a config map. Then you have some metadata. One is name, that's quite obvious, and the other is namespace. Namespaces in Kubernetes serve purpose of isolation of resources. So basically you are able to run multiple applications isolated by namespaces, and the isolation goes as far as security and resource management. Then we have something that's called labels. We label our resources so we can look them up, and we can use them, or we can aggregate data based on these labels. And then we have the data section, which just defines some variables and their values. Other sample, more interesting, is deployment. Deployment is a type of resource which will actually launch your application. This has been very stripped. There is much more to it. It has it might have several tens to several hundreds of lines. That's just as an example. This will run our application, which is referenced by the image shown there, and it will run 3 replicas of our application. Well, basically that's it. Then there are other components within the cluster that are responsible for the deployment being rolled out and being kept alive. Yeah, the resources. Again, not to say it again, Kubernetes is a resource manager. And here are some base resources that are included in every cluster. And we're going to talk about it a little. First, we have Node. Node is the most basic resource. It's basically the physical machine or the virtual machine that is part of the cluster, and it's represented as a node resource. Then we have namespaces, which provide isolation between applications. And then we have pod. Pod is kind of the smallest resource in Kubernetes, and it wraps containers. So if you're deploying your application, you might say you want to run 5 pods of your application. That means there will be 5 instances of your application running, and handling 5 times the load as one would. Then we have deployment, which we've seen a while ago. And this resource describes the entire deployment and how it should behave. It basically describes behavior using which pods should be deployed on the worker nodes. Stateful set is basically pretty much the same as deployment, but it's targeted for stateful workloads. That means databases, message queues, or other applications which require stable storage, stable network identity, and it's just more kind of static. There are different rules on how these applications are restarted, for example, because in stateless deployments, if you have 8 pods running and you decide that you want to update your application to a newer version, the strategy would be, for example, that two of the pods at a time go down and are replaced by newer ones. And by the default strategy for stateful set would be that one by one application is restarted. Just an example. Config map, which stores configuration files or parameters. Then there are secrets, which are basically the same, but are designated for sensitive data and are not as easily accessible as config maps. Another very important resource here is a service. When you deploy a resource of type service, you define an endpoint in the cluster where communication should take place either from inside the cluster or from outside. Service then, by definition and by use of labels, routes this traffic to pods that match those labels. So if you deploy 5 pods of your application, you deploy a service along with it, and the service will ensure that the components in the cluster, in this case, most likely kubeproxy, will be routing the traffic to the right pods. There is a special kind of essential resource, and that's Ingress. And Ingress basically creates a publicly accessible endpoint for HTTP or HTTPS traffic. The difference between Ingress and service is that it's really meant for HTTP traffic, and it also supports TLS and several methods of let's say, certificate generation, automatic DNS updates, and yeah, the behaviors it could have are limitless. Within this presentation, I prepared a demo which will be available to all of you at the end. It's a GitHub repository where you have all of this that we've been talking about kind of ready to use or to experiment with. And what did we use? It's basically a kind of case study. We started with DigitalOcean. I chose DigitalOcean for the obvious reason it's the cheapest and also very easy to handle. Within DigitalOcean, we'll be utilizing several resources. First of all, of course, it will be a Kubernetes cluster, which will be provisioned as a managed Kubernetes. We'll be using their DNS service, so we can set up host names for our application, using which the users could access the app. And we'll be using their load balancer, a managed load balancer, which will basically create a public IP address for us and route the web traffic back down to our cluster. And we'll be using block storage for our database and for our caches. So here you basically can see that DigitalOcean, for example, can do this for you for a few tens of euros a month. And yeah, you don't have the hassle of setting this up yourself. Within the cluster, Kubernetes itself still requires some components that you need to run to make it fully operational and production or workload ready. And this, what we will see, is just a sample stack up of applications that you can install. For most of these, you have tens of options. And why I chose these, it's just experience, and I have a good experience with these components. First of all is metrics server. This is one you don't have much of a choice. What it does, it basically collects usage information from your nodes and from your pods. So you're able to see CPU utilization, memory usage of the resources in your cluster. The next application is Ingress Nginx. Nginx is a very well-known web server and a Riwers proxy. This app, as Ingress Nginx, will basically handle the ingresses and route the traffic using HTTP reverse proxy to our workloads. Another application we'll be deploying as a base for our cluster is external DNS. What this does is that when we create a ingress, it will automatically find out which service is back in it, and it will automatically create DNS records for our service. So we don't have to do that manually. Then we will be deploying Cert Manager. It's a automated certificate manager, which alleviates you of the hassle of managing TLS certificates. What this component does, it again takes the ingress resource, it looks at the host name, and it uses an external service, for example, Let's Encrypt, to automatically issue a certificate for your service. So yeah, it's green in all browsers. And also it takes care of renewals. So yeah, you don't have to do anything. You just deploy this and you're good to go. And the last application in our stack, which we'll see, is ArgoCD. ArgoCD is a continuous deployment platform or continuous deployment tool, which takes care of your applications and makes sure they're running properly, and monitors them, and provides a very nice user interface so you can see what's going on with your apps. Okay, to make this even more complicated, we won't be doing this by hand. We'll use Terraform. Terraform is the infrastructure as a code tool, which allows you to deploy these resources in a quite simpler way, and in a way you can reproduce this very easily. Terraform will be deploying the cluster for us, the DNS domain, and it will be deploying all these releases to the cluster. So we will just write, it's like 7 files of from 10 to 100 lines of code, or maybe 10 to 50. And all of this is done for us. So we'll be using DigitalOcean managed services, some base Kubernetes applications, and there's one more magic word, and that's Helm. Helm is something of a package manager for Kubernetes. As we were talking that Kubernetes is based on resources. So you create resources which are YAML files that have some structure. What Helm does is takes these resources, provides some level of templating, so you can customize the values from deployment to deployment very easily, and then renders these resources and applies them to the cluster. So you can create something called a Helm chart for your application, where it's kind of a template of your app, and then you can deploy it 7 times with different parameters, with different host names, with different configurations. Back to the Terraform for now. For example, this, I think 11 lines of code is all you need to write to create a Kubernetes cluster in DigitalOcean. So it really simplifies things. Something you would be clicking through the UI for 5 minutes, you just write it here. Okay, clicking one time through their web UI wouldn't be so bad. But if you plan to reuse this in other environment or create more clusters, or you just want to have this managed in one place, this is the way to go. So as we were talking, it's Terraform allows us definition of cluster resources as a code. It manages these resources for us. What this means, that if there is a drift, so for example, something changes outside in the cluster resources, it will detect these changes and can correct them back. Also, when you update the code, the Terraform code of your resources, you will just hit apply, and it gets updated very quickly without you having to do it manually. This might seem kind of unnecessary, but imagine you're managing 30 clusters, that are supposed to be almost identical, but with some changes. You want to change one thing, one small configuration thing, you have to do it 30 times through some gruesome user interface. This way, you will just write it once, apply it, and it's done. So that's why Terraform. we were talking about Helm, but I think I already told everything that's in this slide. So yeah, Helm provides us with kind of templates or complete packages of our application that can be customized and deployed in multiple environments. And yeah, here's ArgoCD, which is a continuous delivery platform that takes care of our application, takes care of the Helm renders, takes care of the values we put in. It monitors the state of the applications. It provides a very nice user interface for this. And yeah, that's basically it. So when we do the Terraform apply over our project, what's nice about this is that it does the following for us. It creates the cluster for us. It sets up DNS. It installs metric server, the external DNS controller, the server manager, ArgoCD, and then at the end, it deploys our application to the cluster using ArgoCD. Yeah, the nice part is that you'll be writing this for 30 minutes, but you will have it done and applied and running in under 10 minutes. And yeah, basically, here are just some screenshots of the ArgoCD I mentioned. I'm not sure if you cannot see it, but people online can. Basically, here what you can see here are the resources you deployed, their relationships, and their states. And those are the most important things you need to see here. You can also manage the applications from here, but in our sample, we're doing that using Terraform, which will ensure consistency even over multiple environments. And here is again a very nice view where you can see the full networking of your application. You can see the IP addresses using which clients will access the infrastructure. You see the ingress, you see which service it lands to, and you see which bots it will actually finally land on. So I believe that's it from me. As I said, for this demo, I have prepared a repository. You can all access, use, observe, I don't know, do whatever you want with it. The presentation is included. And yeah, I believe that's all from me. Adam?
Okay.
I don't know if we have any questions.
Yes, let's get to questions. All right. Thank you, Lubo. It was a very good presentation. So, let's go through the questions which we have right now on Slido. And if you have any additional ones, then please feel free to post them. And also, later on, feel free to access this repository. You can find a lot of examples there, which can help you like get into the topic a little bit more. So, should I be worried that I have no idea how to set up K8s, the DIY way, and only can use the managed solutions? Could you provide an example in favor of DIY?
Well, no, definitely should not be worried, but it also depends on the use case. For most cases, the managed Kubernetes is a good choice, but sometimes you might have just so much workload that it would get cheaper if you go to on-premise solutions, because cloud-based solutions, especially let's say AWS, tends to really rise in its costs as you grow. And using on-premise hardware can be cheaper, and also if you're, let's say, infrastructure provider or data center provider, you have a lot of your own hardware. So why would you pay extra for managed services? Yeah, if you don't need extra availability zones and availability in multiple regions, if you have your own bare metal, and you don't need to pay anything extra for managed services.
Of course. Okay. So Peter is asking, I use Docker Compose YAML to spin up containers for local development. Is there a similar way to use K8s for local development? Is the common practice?
Yes, there most definitely is. Even if you take the very first go-to application called Docker Desktop, which you run on your machine, it has built-in Kubernetes, which you can just launch. It's somewhere in the settings. You can very easily then just install few of these components we were talking about, and you have a working one single node cluster, which is kind of an oxymoron, but yeah, but you have it running locally and you can develop directly using Kubernetes. And it's a very common practice these days.
There you go. So Andre is asking, what is the best suggested approach to manage environment variables as shared config for couple 3 to 5 services in a Kubernetes cluster?
Shared variables. Yeah, well, basically you can create a config map for this, but it really depends if these variables are should be in the same namespace or not. If they are in the same namespace, you can just use the same config map and mount it as or secret and mount it as a volume to all the pods in multiple services. If they're not in the same namespace, yeah, well then you will need some magic around it. But this can be, for example, achieved using ArgoCD and Helm, where you can generate the same resource in multiple namespaces. There are several approaches on how to do this, but yeah, I would suggest the easiest one is to put it all in one namespace.
Cool. So, do you have experience with alternatives of Kubernetes? What are advantages and disadvantages?
I don't really know what kind of alternatives we could be talking, but there's ECS. Yeah, a Nomad. Yeah, I don't have experience with it, but we like to refer to it as a poor man's Kubernetes, because it basically just takes lots of machines and allows you to deploy very similar workloads on it. Kubernetes is much more complex in terms of what you can do with it. Again, I'm going to say it's a resource manager. This means that you can extend it and use it for much more wider surface of use cases than just running applications. Well, for example, Nomad is only designed to do such. Then you have, for example, AWS ECS, which allows you to run containers directly in cluster without the need to run all this complex infrastructure. But honestly, I don't have experience with that, so I'm not gonna talk about it anymore.
Of course. So, the next question is coming from Victoria. How do you manage dev, stage, and prod in Kubernetes? Do you use separate clusters or just namespaces? What would you think works the best?
Well, again, that really depends on the use case. For example, on the project we're working on, we have separate clusters for this. And again, there is a mixture. For example, we have one kind of big development cluster when we run all the development environments. All the applications are separated by namespaces. And yeah, that's basically it. For staging, we have one big cluster where several staging environments run. But for some customers, we have separate clusters for staging environments because they require it. And for production, it's the same. Yeah, there's one large cluster which runs most of the smaller application sets. And then we have several production clusters for customers who demand it. What would I suggest? If it were me, I would just create one quite large cluster where you separate your workloads using namespaces, network policies. You have all the tools you need to make it secure, and it's much easier to manage one large cluster, than manage 30 clusters.
So another question is from J Diesel. I haven't heard anything about AI. Is that by mistake? Or really does not have anything to help with here? That's your favorite topic, Luvo, so.
Yeah, so my answer to this would be what you've seen here. It's an honest work. Yeah. If you want, if you want to fake it with AI, do it.
But really, like he prefers to do everything manually, so this is
Yes, because I want to know what I'm doing.
So then, but have you at least tried it on in some cases, or like do you think that
I tried AI a few times. For example, when I needed to format a bullet list into a table. Yeah,
or read happy birthday wish?
I don't do that.
Okay.
I do the personal.
So another question is from Marcel. Uh, from what size of project? And he wrote it like t-shirt sizes, like SML.
That's quite well.
You recommend to use Kubernetes in the matter of complexity and price.
In nowadays world, I would suggest to use it from the beginning because the entire software world is really skewing towards containerization and Kubernetes, and it allows you to write your application in a way and prepare it to be deployed in various environments. So, yeah, these days I would just suggest start like it.
Mm-hmm.
Okay, if you're running, for example, I don't know, your shopping cart, a shopping list app for your family, run it in a Docker Compose and in a VPS. But if you're developing an application which should be consumed by more people than just you at home and your wife, you should definitely start by containerization and I would go cloud native, so Kubernetes.
What are the advantages of using OpenShift? Can we achieve the same result with KDS and ArgoCD? ArgoCD.
Agora. To be honest, I don't have any hands-on experience with OpenShift, so I don't really know what the advantages of OpenShift should be. But I really think you can achieve this using pure open source tools.
Well, now we have another good question from your AI friend. Are there APIs so I could define the infrastructure in English when then use AI and it will bootstrap it all?
Come again?
So if there is like a tool where he will just describe and to generate I just already marked the question, but
I'm not sure if there are specific tools to that would allow you to enter a prompt and get resources generated. But I'm pretty sure if you even ask ChatGPT, it will do this for you. But yeah, from my experience, it will do it in AI quality. So you should really double check what you're going to deploy. But yes, AI tools can do this. Yeah, the large language models know about this, and they can create Kubernetes resources, even charts. So yes, it's possible.
but remember it was trained on your code, so I don't know if you want that. So
Careful.
another question from Victoria: do you use any standard labels to organize your apps in Kubernetes? Any popular conventions to follow?
Yes, there is a page directly on Kubernetes IO documentation side which lists the most common labels that should be used. It's like Kubernetes IO/instance, name, app, etc., which basically categorizes a replication. And when you're using tools like Helm or ArgoCD, it will also automatically add some labels to distinguish the applications between themselves. What we also like to do is to add custom labels from on the project to, let's say, categorize it to some area, whether it's related to business or infrastructure, name the responsible team or name the responsible person so that you know who you should contact if there's problem with some of these components, or to forward alerts to the right person or a group of people.
David is asking, what will happen if my connectivity to the cluster fails while running Terraform apply?
A lot of things could happen. That could go very magical. Actually, yeah, it really depends in which state this happens. For example, it can happen while the resource on the other side is already being created, but you cannot write it in your state because you didn't yet receive response for the resource creation. Well, unfortunately, there isn't much to do then. You just have to examine the situation. So if you find out that, for example, the Kubernetes cluster in DigitalOcean is already spinning up, but you don't have it in your Terraform state because your connection has broken up, there are two things you can do. You can wait for the resource to create, and then you can import it, because Terraform supports importing resources. So if it doesn't know about it, you can just use Terraform import command and you get it in your state. The other thing is, you can do, you can delete the cluster and run the Terraform again, for example.
See, there's a solution for everything. Then we have another question. What requires managed Kubernetes from the developer, so the DNS certificates are included?
The provider you're using should allow you to modify DNS records via API. For this, in this case, we were using the controller called external DNS. The external DNS controller connects to the API of DigitalOcean, and while verifying the host, it will insert a special text record in the DNS. And Let's Encrypt servers can verify that you're owner of the domain. Yeah, basically that's it. And for example, if you have AWS has their own certificate management. They can provide the certificates for you. It's free. And you could connect the cert manager directly to, I don't know if it's possible, to AWS, or you can use their service in many other ways. So the provider needs to give you the ability to manage DNS, but you don't even have to have that. You just need to point the traffic to your server, and there is another method of validation. It's called HTTP-01, and it will allow you to validate that you're owner of the domain just by Let's Encrypt servers talking directly to your web server. So there's several ways to achieve this.
Why don't you run for a so you can see?
I'm not that brave. It's already applied. It's running. So
Go on.
I can do it.
We have
Continue with questions.
the questions are coming up actually. So another one, is your demo like a boilerplate? I can use it to start up a fresh project.
Not basically, it could be used more like as an inspiration. You have a application with totally random behavior that's described there. You have Docker file for it, which builds the container image. You have development Docker compose included in there. You have the Helm chart included, which includes some more advanced things like pre-installation hook jobs, which generate some cryptographic material and stuff like that. There's something you can get inspired from. You have a Docker compose ready for kind of production. And there is a complete Terraform repository, which if you just change 4 parameters in configuration, you can run it on your DigitalOcean account and you will be able to deploy the infrastructure. So yes, you can use it as a boilerplate, but it's not like a template where you just fill in your data.
Mm-hmm.
You can use it for inspiration.
Feed it to AI and then
feed it.
it will help you finish it. Okay, so the last question. You mentioned that that single node cluster is an oxymoron, but if we only want scaling of pods on a single machine, isn't such cluster a good choice?
Yes, it might be. And for small deployments, single node cluster is really a legit design. But cluster should consist of more than one of something. That's why I call it an oxymoron.
All right. So I guess that's all the questions. Thank you very much, guys. And thank you, Lubo, for a great presentation.
Okay. Thank you.
This was Lubomir Kaplan. He's our senior DevOps engineer. My name is Adam Bilicic. I am the CTO of Riwers. And if you are watching this later, then at the end of the video, you will see my contact information. You can just scan QR code and get in touch with me. So thank you very much for everyone joining online and also in person. And I guess see you in the next Tech Talk.
Also, thank you very much. And in case you would have some more questions, feel free to reach out.